Oke, kita akan belajar algebraic geometry dari Richard Borchard.
The first example is the problem of Pythagorean triangles. As everybody knows, right-angled triangles satisfy Pythagoras' theorem, where the sum of the squares of the sides is the square of the hypotenuse. So we have the usual 3, 4, 5 triangle as the simplest example. So this leads to the following problem. How can we classify all Pythagorean triangles? So there are several ways of doing this. I'm going to discuss an algebraic way and a geometrical way. So first of all, let's do the algebraic solution. So we want to solve x squared plus y squared equals z squared with x, y, and z integers. So here's the algebraic solution. We may as well assume that x, y, and z are co-prime, because if any two have a common factor, we can just divide out by it. If we look at the equation mod 4, we know that x squared, y squared, and z squared are all congruent to 0 or 1 mod 4. And since they can't all be even, we see that z must be odd, and one of x, y must be even, and the other must be odd. So we may as well take y to be odd without any loss of generality, and x to be even. Then we can rearrange the equation as y squared equals z minus x times z plus x. And we notice that these two numbers are co-prime. Since x and z are co-prime, the only possible common factors of these two numbers would be 2, but since z is odd and x is even, they can't have a common factor of 2, so they're co-prime. Now, if we've got two numbers that are co-prime whose product is a square, then both the numbers must be squares, at least opt to sign. So by changing the sign of this, if necessary, we can assume that this is a square, say r squared, and this is a square, say s squared. Well, then we can solve for z and x. We find z is equal to r squared plus s squared over 2, and x is equal to s squared minus r squared over 2, and y is equal to rs. Here, r and s will be odd and co-prime. And for example, you can read off some solutions. So if r and s is 1, 3, or 1, 5, or 3, 5, then we find the solutions 3 squared plus 4 squared equals 5 squared, or 5 squared plus 12 squared equals 13 squared, or 8 squared plus 15 squared equals 17 squared, and so on. So that's a perfectly good solution, but it's not completely satisfactory. It's slightly messy because we've had to pick one of these numbers to be odd, and we have r and s must both be odd, and so on. So it's a slightly messy. So that's the algebraic solution. Now we're going to discuss a geometric solution in the style of algebraic geometry. For this, we want to solve x squared plus y squared equals z squared in integers. Well, integers don't work terribly well geometrically. So let's instead put big X equals X over Z and big Y equals Y over Z. And then we find X squared plus Y squared is equal to 1, with X, Y rational.
Oke, jadi solusi geometri.
And I guess you all recognize this equation. It's just the equation of a circle. So what we're trying to do is to find rational points on a circle, where a rational point is, of course, one whose coordinates are rational. Now, since we've made this geometric, we can draw a picture of what is going on, and it just looks like this. So here we have a unit circle, and we're trying to find rational points on it. And there's a very simple way of doing this. What we do is we pick this point here, and here we have some point with rational coordinates x, y, and we just draw the line through x, y, and this special point -1, 0, and it intersects the y-axis in a point 0, t. Using t instead of y because I've already used y for that. So if you look at this for about very briefly, you notice that t is just the slope of the line. So the slope is equal to t. And we can calculate t. We see that t is just y over x plus 1. And conversely, so if we're given x and y, we can construct a rational number t, and conversely, given t, we can find x and y, and these will be got by solving some quadratic equation, and we know one of the roots of the equation is rational, so the other root must also be rational. Anyway, we can do this explicitly as follows. So we know y is equal to t times x plus 1, and substituting in, we find t squared
Hold on.
squared plus x squared equals 1.
Gimana katanya? Saya tadi rada ngeblank. Jadi kita ingin semacam memparametrisasi poin titik-titik di lingkaran. Oke. Kalau dia lewat titik min 1,0 dan 0,t itu adalah ya garis yang lewat apa? Lewat min 10 sama 0,t. Samaan garisnya apa? Y sama dengan t dikali dengan x tambah 1. Atau t sama dengan y per x tambah 1. Terus ngapain? Kita inginnya dapat y dan x-nya. I think I have seen this before. Oke, mau ngapain dia sebetulnya? Sebentar. Lanjut.
Rearranging it slightly, we find x plus 1
Oh,
t squared
nyari,
plus 1.
pengen nyari apa? X dan Y dalam T ya. Jadi kalau dilanjutin dari sini, x kuadrat ditambah y kuadrat t kuadrat x tambah 1 kuadrat sama dengan 1. Kemudian ini x kuadrat ditambah t kuadrat x kuadrat tambah 2x tambah 1. Berarti x-nya itu kalau pakai rumus ABC atau kita bagi dengan x. Oh, ini kan kayak itu apa? Kalau substitusi tangen X per 2 sama dengan T kayak gini. Berarti apa? X dikurang T pangkat 4 per board manul apa kerjanya cepet. Berarti X sama dengan min T kuadrat per 1 tambah T kuadrat plus minus 1 per 1 tambah T kuadrat. Ini berarti kalau kita pilih T-nya rasional, maka kita punya X-nya rasional. Kalau X-nya rasional, berarti Y-nya rasional. Pertanyaannya, apakah kita sudah mendapatkan semua titik rasional di lingkaran? Jadi sudah semua titik rasional di lingkaran. Ya, mungkin ini perlu dipikirkan lagi. Oh, sudah. Kenapa? Karena kalau misalkan ini titik rasional dan ini rasional, maka slope-nya akan merupakan suatu bilangan rasional juga. Ya, jadi berarti dengan cara seperti ini, kita sudah bisa mendapatkan semua titik rasional di lingkaran. Kalau kita punya semua titik rasional di lingkaran, berarti kita ya bisa punya semua solusi Pitagoras, kurang lebih seperti itu. Oke, kita lanjutkan.
X plus t squared minus 1 equals 0.
Oke, kita speed up.
And there's factors, and of course x plus 1 is just this point here, which we're not really all that interested in. And this root here corresponds to this point here. So we find x equals 1 minus t squared over 1 plus t squared, y equals 2t over
Bisa
t
difaktorin.
squared.
Sorry.
And obviously big X and big Y are both rational if t is rational. So what we have
Stupid
here
me.
is
Okay.
a correspondence between points on the circle.
Bentar. T dikali itu sama dengan 0. Oh, X kuadrat min 1-nya difaktorin jadi X kuadrat tambah 1. Oke. This is not good manipulation. Jadi dari Jadi kita punya Y sama dengan TX tambah 1. Kemudian kita punya X kuadrat ditambah Y kuadrat sama dengan 1. Ini ditulis sebagai X tambah 1, X min 1 ditambah T kuadrat X tambah 1 kuadrat sama dengan 0. Ini X tambah 1, X min 1 ditambah T kuadrat kali X tambah 1. Satu tambah T kuadrat X ditambah T kuadrat min 1. Jadi X-nya min 1 sama X sama dengan, kayaknya salah saya ngitung tadi. 1 min T kuadrat per 1 tambah T kuadrat. Dan katanya, oke, min 1 itu berkorespondensi dengan titik yang ini, kemudian satunya lagi titik yang ini. Oke, kalau ini dapat, berarti Y-nya juga tinggal dikalikan dengan X. Oh, ini ditambah 1. Y-nya T dikali dibagi dengan 1 tambah T kuadrat. Jadinya 2T per... Ya, oke. Alright.
They almost correspond to points on the y-axis. Well, they don't quite correspond because there's one slight problem. If we chose this point here, then we would kind of be trying to find the intersection of a vertical line with the y-axis, which doesn't really work. So this is the points on the circle which are not the point -1, 0. So we almost have a one-to-one correspondence between the circle and the y-axis, a straight line. In algebraic geometry, this is called a birational correspondence, or birational equivalence. So a birational equivalence roughly means one that is an equivalence except on subsets of codimension at least 1. If you're doing something like studying smooth manifolds or differential geometry, then this notion of birational equivalence is kind of stupid, because if you take two reasonable smooth manifolds of the same dimension, then you're allowed, and you can throw away a codimension 1 subset of both of them in order to make them both just a union of balls. So this concept is uninteresting for smooth manifolds and is a characteristic feature of algebraic geometry. This correspondence between the line and the circle is also used in calculus. Here it's called the Weierstrass substitution. The Weierstrass substitution is one used for evaluating integrals of some function of sine theta and cosine theta. So what I'm going to do is I'm going to take
That's exactly
this point x, y.
With
this
cosine,
angle is theta, then x is equal to cosine of theta, and y is equal to sine of theta. And t can be worked out because if you remember Euclidean geometry, you can see this angle here is theta over 2. So t is tan of theta over 2.
Stop dulu.
And now you may recognize the Weierstrass substitution. You remember if you've got an integral involving cosine theta and sine theta, you put t equals tan.
Katanya gimana? Sebentar, boy. Jadi ini memang familiar ketika kemarin pas substitusi. Ini katanya kita buat di sini theta, maka si x ini akan jadi cos. Kemudian ini sudut keliling, jadi ini theta per 2. Berarti si slope-nya T-nya adalah sama dengan tangan X per 2. Oke, jadi kalau T-nya tangan X per 2, jadi X-nya bukan yang ini. Ini sama dengan sin theta, yang ini adalah cos theta. Apa tadi namanya? Weierstrass substitution. Jadi ini kegunaannya adalah kalau kita punya integral sebagai fungsi rasional dalam sin dan cos, bisa kita ubah menjadi integral dalam fungsi rasional t saja, dan kita bisa gunakan pecahan parsial untuk menyelesaikannya.
Theta over 2 and turn cosine theta and sine theta into these rational functions of t. So any integral of sine theta and cosine theta can be turned into an integral of some rational function of t. In calculus textbooks, this is obviously presented as this really mysterious, puzzling substitution that comes from nowhere at all. But from algebraic geometry, it's clear where this substitution comes from. It's simply the easiest birational equivalence between a straight line and a circle. So what you're doing is you're turning integrals over a circle.
Birational equivalent itu katanya. Oh, ada korespondensi satu-satu. Okay, let me try to understand this. Birational equivalence. Ini korespondensi satu-satu antara lingkaran. Ini situasi khusus ya. Lingkaran minus titik min 1, 0. Jadi setiap kali kita jadi kita bisa punya korespondensi satu-satu antara titik pada lingkaran yang ini dengan titik pada garis. Setiap kali kita bikin garis semacam ini, kita mengkorespondensikan atau mengkaitkan antara suatu titik di sumbu Y dengan suatu titik pada lingkaran. Kecuali titik yang ini. Jadi ada korespondensi satu-satu antara titik pada lingkaran kecuali titik min 1,0 dengan semua titik yang berada pada ini. Oke.
Into integrals over a straight line in the simplest possible way. Anyway, we should just have a quick example. So what this says is if you choose a rational number t, you get a solution to, you get a Pythagorean triangle. So let's try t equals a half. Then we see x is equal to 3/5, y is equal to 4/5. So we get the solution 3 squared plus 4 squared equals 5 squared. And similarly for other rational values of t. Well, treating this as a geometrical problem rather than an algebraic problem gives you additional insight into the solutions. In particular, circle forms a group. In fact, you can identify it with just the group of rotations of the plane fixing the origin. And we can work out the group operation fairly easily. For instance, suppose you've got 2x1, y1 and x2, y2, and you wish to multiply them by the group operation. Well, this is just x1, x2 minus y1, y2, 1, y2 plus x2, y1. Where does this formula come from? Well, it's just the well-known formula for the cosine and sine of a sum of two angles. So we can think of this as being cosine theta 1, sine theta 1. When I say it's well known, I mean it used to be well known. Of course, nobody memorizes these things anymore. So this is cosine theta 2, sine theta 2, and this is just cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. And I'm not only getting a bit bored of writing this out, but I've run out of room, so I'll leave you to fill in this one. So of course, this is just the well-known formula for cosine theta 1 plus theta 2. So here we have the addition of angles, which is the group operation of the circle, corresponds to this operation on the circle in rectangular coordinates. This is one of the simplest examples of something called an algebraic group. So informally, an algebraic group is a group whose group operation is given by polynomials. So here the polynomials are that and that. There's another way of thinking of algebraic groups, or for that matter, algebraic varieties. You can think of this as being a functor from rings to groups. I'll explain what this means. Suppose we take any commutative ring R. Pretty much all rings in algebraic geometry are commutative by default. Then we can map this to the set of pairs x, y in R squared with x squared plus y squared equals 1. And now we can define the group operation by this formula here. Well, we should, of course, also have an identity of the group, or the identity we can just take to be the point 1, 0, and the inverse x, y inverse is, of course, just going to be x
grupnya
minus y.
R kuadrat.
And you can easily check that if R is any commutative ring whatsoever, then the set of solutions of this equation forms a group under these operations. For example, if we call this algebraic group G, we can ask what is G of the complex numbers. So if we put the real numbers in here, we just get the unit circle. So what would the analog of the circle be for the complex numbers? Well, it's the set of points x squared plus y squared equals 1 with x, y complex numbers. So let's see if we can figure out what that is. Well, that's easy enough, because over the complex numbers is factorizes as x plus iy times x minus iy. And we can set x plus iy equal to z, in which case this is equal to z bar. It's not z bar, it's equal to z minus 1. So all we have wanted the set of complex numbers that have an inverse. So this is the set of non-zero complex numbers z. So the circle group, you can say its real points are just the usual circle of radius 1, say, and its complex points turn out to be, you can identify them with the group of non-zero complex numbers. So to summarize this example, we have seen several different ways of thinking about a circle. So it's just ways to view a circle. So first of all, we can just think of it as being a subset of the real plane. Secondly, we can think of it as being a polynomial, x squared plus y squared minus 1. And of course, if we've got any collection of polynomials in several variables, we can think of them as being a subset of some vector space. So the set of zeros of such a collection of polynomials is often called an algebraic set. Thirdly, we can think of the ideal generated by x squared plus y squared minus 1 in the ring of polynomials in 2 variables. So this ideal is, of course, just the ideal of all functions that vanish on the circle. So we can try going from ideals to subsets of space. So we just, if we're given an ideal, we can take the set of all common zeros. And conversely, if we've got some subset of the plane, then we can look at the ideal of all polynomials vanishing on it. We'll be discussing this in much more detail in later lectures. Well, if we've got an ideal, we can take a quotient might. So we can look at the ring Rxy modulo this ideal. This is called the coordinate ring of the circle. And we can think of this as being a collection of all functions on the circle. Well, you may think it's not all functions on the circle, but if you're an algebraic geometer, it is all functions on the circle, because the only functions we're going to allow are going to be polynomials. So this is the set of all polynomial functions on the circle, which are the only functions algebraic geometers are really comfortable with. You can also think of this as being a smooth manifold. So one thing you can do in algebraic geometry is pretend that things are smooth manifolds and start applying methods of differential geometry to this. Well, this doesn't always work, because in the first place we want to work over fields like finite fields where smooth manifolds don't make a whole lot of sense. And secondly, as we will see fairly soon, you can also have solutions of equations that aren't smooth. Number 6, we can think of this as being a group, or rather an algebraic group.
Okay, wow.
So algebraic group theory is quite a big area in algebraic geometry. And another way of looking at it is as a functor from rings to groups. Or sets, if we don't want to think of it as being group. So this is a very powerful method of studying algebraic sets, introduced mainly by Grothendieck.
Okay, thank you. Dah dulu.
So this is the second part of the first lecture in which we will discuss some cubic curves. The first cubic curve we will discuss is the curve y squared equals x.
Ya, begitulah. Jadi apa yang kita pelajari? Jadi paling tidak tadi contohnya soalan aljabar bisa dilihat sebagai persoalan geometri. Nyari solusi persamaan Pitagoras sama aja dengan nyari titik rasional di lingkaran. Sedangkan si lingkaran itu sendiri bisa dilihat dalam berbagai cara. Beda ya yang field medalist cara ngajarnya. Oke, itu aja lah. Ini ada yang nonton nggak? Saya nggak terlalu ngecekin komentar. Oh, nggak, ini masih dasarnya juga nggak dasar amat. Tapi mungkin ini kita melihat dari perspektif Richard Borchardt, karena kalau kita ngikutin buku teksnya aja mungkin kita nggak bisa memahami apa ide besarnya sih sebenarnya di algebraic geometry itu yang sebenarnya yang saya kurang nangkep, karena selama ini saya melihat algebraic geometrinya dari sudut pandang aljabarnya aja. Jadi kayak ideal ya seperti yang tadi dikatakan Richard Borchardt. Tapi saya nggak tahu masalah mula-mulanya apa. Sebenarnya kan mungkin masalah kalau algebraic geometry itu adalah geometri yang pakai aljabar. Jadi permasalahan utamanya adalah permasalahan geometris yang diselesaikan dengan menggunakan aljabar ya. Nah, yang saya nggak ngerti itu persoalan geometris seperti apa, sehingga dengan menggunakan pendekatan aljabar ini kita punya tools yang banyak untuk menyelesaikan masalah itu ya. Mudah-mudahan saya bisa selain bikin video untuk ngasih materi ya, saya juga ingin belajar sesuatu juga ya. Begitu aja, makasih sudah nonton.